Let z equal the inverse tangent of y over x, and let x equal r cosine theta and y equal r sine theta. So this is the standard polar coordinate transformation from rectangular coordinates x, y to polar coordinates r theta. And we'd like to find the partial derivative of z with respect to r and the partial derivative of z with respect to theta using the chain rule. And then we'll do the problem again by first writing z directly as a function of r and theta and comparing our answers. So before we get mired into the details, we have to work with the function inverse tangent of x, and we also have to work with the function 1 over x. And so let's just quickly recall their derivatives in the one variable setting. The derivative of inverse tangent of x is 1 over 1 plus x squared, and the derivative of 1 over x is negative 1 over x squared. This one comes from rewriting as x to the negative 1. And when we take the derivative, we use the power rule, and we get negative 1 times x to the negative 2, which is negative 1 over x squared. Okay, so z is a function of x and y. It's the inverse tangent of y over x. And x and y are functions of r and theta. So we'll use the chain rule to find the partial derivative of z with respect to r and the partial derivative of z with respect to theta. So the chain rule says the partial derivative of z with respect to r is partial z with respect to x times partial x with respect to r plus partial z with respect to y times partial y with respect to r. So let's calculate these things. The partial derivative of z with respect to x. So z is the inverse tangent of y over x. The inverse tangent of y over x. The derivative of this with respect to x, we have to use the chain rule because we have an outside function here with the inverse tangent. And the derivative of that is 1 over 1 plus the inside y over x squared, and then times the derivative of the inside. The derivative of y over x with respect to x is negative y over x squared, because the derivative of 1 over x is negative 1 over x squared. And then the derivative of x with respect to r, x is r cosine theta. The derivative with respect to r is cosine theta. And then we have plus partial of z with respect to y. We again have to take the derivative of the inverse tangent, and we get exactly this, 1 over 1 plus y over x quantity squared times, times the derivative of y over x with respect to y, which is simply 1 over x, and then times the derivative of y with respect to r. Y is r sine theta, so the derivative of y with respect to r is sine theta. So there is our derivative. Now let's simplify this. Y over x quantity squared is y squared over x squared. And if I distribute this x squared, I will get negative y cosine theta on the top. And on the bottom, the x squared is going to give me x squared times 1 plus x squared times this quantity. And that's going to cancel the x squared on the bottom. So we're just going to get the nice x squared plus y squared on the bottom. So I really enjoyed multiplying through by x squared here to cancel this x squared. And so I'm going to think of this x, 1 over x here, as x over x squared. X over x squared, that's 1 over x. That way we'll be multiplying through again by an x squared on the bottom. So that's just a nice little trick. So we have plus on the top, we're going to get x sine theta. And on the bottom, we're going to get exactly x squared plus y squared again. And then this is x sine theta minus y cosine theta over x squared plus y squared. Now x is r cosine theta. So this is r cosine theta sine theta minus, and y is y is r sine theta. So this is going to be r sine theta cosine theta. And then x squared plus y squared. X squared plus y squared is r cosine theta quantity squared plus r sine theta quantity squared. So you're going to get an r squared cosine squared plus r squared sine squared. Factoring out the r squared, you get r squared times 1. So this x squared plus y squared is just r squared. But that's actually immaterial here because we probably noticed already that in the numerator, these two things are exactly the same. Whether you have cosine theta times sine theta or sine theta times cosine theta, that's the same. So this subtraction here is just 0. So 0 divided by r squared is 0. And our derivative is 0. So that's interesting. Simple answer. And we might wonder why that was the case. And that's why we have the second part of the problem. Let's first write the function as write z as a function of r and theta directly. So z was equal to the inverse tangent of y over x, and this is the inverse tangent of what is y. Y is r sine theta, and x is r cosine theta. The r's cancel, and sine over cosine is tangent, so we get the inverse tangent of the tangent of theta, which is theta. And so z is just theta, and so the derivative of z with respect to r will be 0, and that's what we got. And the derivative of z with respect to theta should be 1. That we haven't calculated yet. So let's now do the second part of the problem and calculate dz d theta using the chain rule, and we should get 1. So let's recall that z was equal to the inverse tangent of y over x. Y is r sine theta, x is r cosine theta, and we want to calculate the partial derivative of z with respect to theta, and we should get 1. And according to the chain rule, this is partial z with respect to x times partial x with respect to theta plus partial z with respect to y times partial y with respect to theta. And we calculated the partial z with respect to x already. It's 1 over 1 plus y over x quantity squared times negative y over x squared. And now dx d theta, the derivative of x with respect to theta, is negative r sine theta. And then we have plus partial derivative of z with respect to y. We calculated that earlier as well. 1 over 1 plus y over x squared from the derivative of the inverse tangent. And then the derivative of the inside, which is y over x, was 1 over x. And we'll write the 1 over x again here as x over x squared. That was our little trick. 1 over x is the same as x over x squared. We would like to distribute an x squared across the denominator. And then the derivative of y with respect to theta is r cosine theta. R cosine theta. So now let's simplify this. Distributing the x squared across the denominator is going to give us x squared plus y squared in both cases. So I have one big fraction here. The numerator of the first fraction is ry sine theta. Ry sine theta. And the numerator of the second fraction is rx cosine theta. Rx cosine theta. And y sine theta is just r, and x cosine theta is also just r. So this is r squared. Sorry. R sine theta. I did not say that correctly a second ago. So let's correct that. I had my y and my theta backwards there. Let's look at this again. Y is r sine theta. So r sine theta will give us a y. So this is y squared because there's already a y. Plus, and now r cosine theta, this one and this one, make an x. R cosine theta make an x. So x times x is x squared over x squared plus y squared, and this is 1. So there we are. dz d theta is indeed 1. It's r squared. Another way we could look at this is it was r squared over r squared. X squared plus y squared is r squared. Okay, so we have used the chain rule to find dz dr and dz d theta, and then we realized that this function was a very simple function. It was just z equals theta, and so we should get partial derivative of z with respect to r is 0, and partial derivative of z with respect to theta is 1. And after doing the laborious chain rule calculations, we did indeed get these results. So this kind of verifies the chain rule for us.